All right. So, rain shadow effect, ladies and gentlemen, focus up front. Rain shadow effect. This is from last week. Okay? You should have a mountain of some sort. Okay? And we have air. What happens when the air goes up the mountain? What happens to the air? Temperature? What? Okay, so it gets cool. And what happens to pressure as we go up? Right, so if pressure is decreasing, the amount of weight that we're pushing on that cloud is decreasing. What's going to happen to my volume? If there's less pressure pushing on it, it's going to expand, right? So it cools and expands, right? And what do we know about cold water and the amount of water it can, or cold air and the amount of water it can hold? Not a lot. Not a lot. So what's going to happen? Not a lot. Rain. It's going to rain down here, right? Whoa, I don't know what I did. Clearly I clicked something. Okay, so it's going to end up raining. So this side is going to be rainy and wet. We call this the windward side because it gets most of the wind. It's where the wind is going to be hitting first, okay? So it's all the strong wind, and then by the time it comes down here on this side, it's going to be weakened because it already had to go all the way up the mountain. So if we look at this side, what's going to happen to my air then once it goes over this mountain? It's dry. What about temperature? Hot and dry, just like when we formed deserts, okay? So it's going to be hot and dry. We call this the leeward side because it's protected, okay? The leeward side doesn't get as much rain. It's typically dry. It's the sheltered side of the mountain, okay? All right. I did a terrible job of explaining some stuff at the end of yesterday, so I'm going to go over some of that, or on the end of Friday. So I'm going to go over some of it. Some of you were really confused on the Coriolis effect, so I want to talk about that. I have a ball here, okay? It's easier to visualize. When we're talking about the trade winds, okay, I didn't give you a good reason for why the trade winds happen. Okay, or why things deflect in a certain way. So if we look at our diagram of the cells that occur, what's the cell that's from the equator to 30 degrees? What's the name of that? Hadley cell, okay? If I can find it here. All right, here we go. So the Hadley cells right here, Farrell cells here. If you notice, both of these cells have arrows with the air coming down at 30 degrees, right? Because the air, what happens is at the equator, it's going to go up, right? Rains, goes over, and then comes down. So we have lots of air coming down at 30 degrees. So when we talk about the Coriolis effect, okay, we need to look at the air coming down at 30 degrees, okay? So if I'm here, remember the globe turns from west to east, all right? And if I'm spinning this ball, okay, and I start at 30 degrees, my arrow is going to curve down and to the left, right? So if this is spinning west to east and I'm drawing a straight line, it's going to curve down and to the left. Now, if we look at these winds, the trade winds that I talked about, somewhere here clearly, the trade winds here, where do they go? Down and to the left. Same thing that I just showed you on the ball. Okay? If we were to do that going the other way, okay, it would still go towards the equator. It would go up and to the right, okay? So again, if I'm at 30 degrees south and I'm turning this from west to east, my arrow is going to go, right, up and to the left. So this is the reason why we get the trade winds, okay? You can think about them as the Earth rotating, the trade winds like this, okay? The westerlies go up and to the right, Coriolis effect as well there, okay? All right, other thing that I wanted to talk about, ocean currents, okay? First of all, water always flows away from the earth. Okay, we talked about gyres. Okay, if we look at the patterns here, you will notice they follow the same pattern that we just talked about. Okay, if we have my equator, the currents go down and to the left. Now, they make a circle, right? They make a circle, but most of this surface water is going to be following those trade wind patterns, which is the reason why we get them rotating counterclockwise in the southern hemisphere and clockwise here. So if you know about the Coriolis effect, technically you know about the trade winds and you know which way these rotate. If you can piece them together, which I did a terrible job of doing on Friday. Okay. I also wanted to talk to you about, we talked about the garbage patch, right? So this is the Great Pacific garbage patch. A lot of times we get debris collecting here. There are two garbage patches, the eastern and the western. I want to show you an infographic about this garbage patch to get you a better idea of what the heck it is. Some of you might think, oh, Ms. Frankston, it's just like a whole bunch of plastic bottles floating in the ocean. It's not. So we're going to learn about what it is. I'm just going to read through this, zoom in so you guys can see it. So it says, by now, most of us are aware that there's a large patch of floating plastic in the middle of the Pacific Ocean. What you may not know is that it's not made up of plastic bags and empty bottles. It's made up of billions of tiny pieces of plastic. And it's basically invisible unless you're floating in it. While this might sound better, it's actually much worse for the environment and for you. So formation. Of the 200 billion pounds of plastic people use each year, about 10% ends up in the ocean. 70% of that eventually sinks, but the other 30% is carried on the surface by ocean currents. When plastic ends up in the waters of the Pacific, much of it is swept up into the currents that lead to the Pacific Gyre. Garbage from the east coast of Asia takes roughly a year to reach it. Garbage from the west coast of North America takes 5 years. So, contents, what does it contain? 90% of the trash floating in the world's ocean is plastic. In every square mile of the ocean, according to some estimates, floats nearly 50,000 pieces of plastic. In the Pacific Gyre, most of that plastic comes from 4 sources: plastic bags, bottle caps, plastic water bottles, and styrofoam. Okay? So, why should we care? Photodegradation. What does photo mean? Picture, and it also means light, right? Yep. So the sun breaks down plastic into smaller pieces, but it can never break it down entirely. Unlike organic materials, which eventually biodegrade, the plastic breaks into even smaller pieces while still remaining a polymer. As it breaks apart, the plastic ultimately becomes small enough to be ingested by aquatic organisms, which reside near the ocean's surface. Plastic waste enters the food chain. So if we look at the sizes here, it says 39% are larger than 1 millimeter. Remember, a millimeter are those little tiny, the tiniest lines on a ruler, okay? 35% are 1 millimeter wide, 17% are 0.5. So these are all tiny pieces of plastic. It's not like you can actually see giant plastic bags, okay? Lots of estimation. I have no idea. They probably sample and then take that sample and estimate. So they probably sample a whole bunch of things and then figure it out. I'm not really sure. So location, it's located on the North Pacific Gyre, one of 5 major swirling vortices of currents in the world's oceans. How big is it? Borders of the plastic garbage patch are difficult to determine because much of the plastic is in pieces too small to be seen by satellites or planes. Estimates of the size range from about 250,000 square miles, an area roughly the size of Texas, to 6 million square miles, which would mean that the garbage patch covers about 10% of the entire Pacific Ocean. So plastics in the water absorb floating chemicals, which are attracted to the plastic's oil base. Many of these chemicals are known as persistent organic pollutants, which never leave the environment or break down. They include a whole bunch of things. I don't expect you to have heard of any of these, but most of them are pesticides, insecticides, fungicides, basically things used to kill off insects or pests. Okay. And then why does it have an impact? Well, ocean life can mistake the small pieces for zooplankton. When they eat it, they ingest the chemicals the plastic has absorbed. These organisms and small fish are consumed by larger fish, which also absorb the chemicals, which are then eaten by people. Many of these poisonous plastics also end up in the stomachs of marine birds and animals. So we'll talk about biomagnification, but basically it's this idea that as we go up this food chain, those chemicals become more concentrated. Because imagine the zooplankton, right? Zooplankton have a little bit, and then a fish. How many zooplankton does a fish eat in its lifetime? Probably a lot, right? So he's going to have like a lot of that concentration. And then let's say a whale. How many of those fish does a whale eat in its lifetime? A lot. So it keeps increasing as we move up that food chain. All right, last thing. We talked about upwelling. I wanted to revisit thermohaline circulation. Okay, some of you might have this down. I redid the slides, so sorry, you have like absolutely no room for that. Up to you what you want to write of it anyway, because all of this info is in your book. So we said thermo means heat, haline means salt. Okay, so gyres are basically surface currents. Okay, they redistribute heat. So these are gyres, those big swirling whirlpools, right? So they're distributing heat. The thermohaline circulation, these are basically big currents that mix surface and deep water, okay? So whereas gyres are just like moving the surface water, this is mixing deep water and the surface water. This is what Nemo, well, not Nemo, Marlin rode to go find Nemo, right? You guys remember that whole thing? I don't remember what they even called it.
It's called
something Trans-Pacific Highway, I don't know, whatever it was. Okay, this is what they rode to get there, all right? And what you see here is that at the equator, we get a lot of heat, okay? Well, as that water moves up to the north or to the south where there's cold stuff, right? If it hits this iceberg, it's going to be cool. We know cool water is more dense, so it's going to sink, right? So that's what this blue arrow is showing. It's sinking, right? So it's down the bottom of the ocean. And as it comes back, it's going to come back up to the surface. We know that there are a lot of nutrients down at the bottom of the ocean. So if we're getting a lot of mixing from the top and the bottom of the ocean, we're mixing nutrients. We're also redistributing heat, okay? The other thing that helps with this is freezing and evaporation. As water freezes or approaches freezing, it gets saltier and it drops down to the bottom of the ocean. Or as water evaporates, okay, the water that's remaining gets saltier, okay? So it distributes different nutrients. I have like a 50-second video clip of a demonstration that somebody did that we can watch. And they're just showing an example of this, possibly. So what they have is an iceberg, or like a big ice cube, in this tank. Okay, so we've got like salt water here, and we've got a big ice cube. And what they're going to do is they're going to add food coloring. Okay, so that's showing like water, and you'll be able to follow that food coloring as it goes through and hits that iceberg. So circulation, thermohaline. So we've got our ice. So they're just going to put a drop of food coloring, maybe. So they have a drop of food coloring, okay? Now, as this food coloring hits that ice, it becomes cold, right? We know cold water sinks, okay? So cold water sinks, and basically this is what's happening throughout our oceans, is we have water sinking, and then eventually it'll rise back up, and it's this big conveyor belt, okay? You guys saw how that moved. It's just like a conveyor belt. It redistributes heat from our... When they talk about the climate change, stopping this conveyor belt, they're talking about the polar ice caps melting, and then those polar ice caps, and basically the ice up here, drives a lot of that sinking, right? And so they're worried that if all of the ice were to melt, right, it would actually get rid of this whole current, this stream, this heat pump that we have. All right, last thing we're talking about, El Nino, okay? So we talked about the fishies. Before you like write any of this stuff, what did we talk about the fishies on Friday? What happened to them? Okay, why? Why did they end up dying, a bunch of them? What happened to the weather? How? Did the water get warmer or colder?
I got warmer.
See, the water got warmer, right? So remember we talked about the fish. They liked that cool water coming up.
Okay, so this is what happens. The water got warmer.
Uh-huh.
There wasn't enough plankton or food for the fish to survive, so they weren't able to reproduce. That's what happened.
There you go. All right. So the water got warmer. We didn't have that upwelling. Remember we talked about upwelling where we've got water coming up from the surface? Okay. So you can see that kind of in this picture here. So the upwelling here, water coming up. Okay. This is because these trade winds go to the west. We talked about the trade winds, right, with the Coriolis effect. So they blow to the west, right? And because they're pushing all of this hot water over here, it creates a deficit here, right? We have like a vacuum, and we got to have water come up and fill that vacuum. So the cold water comes up, and it brings nutrients with it. Now, the little phytoplankton are happy because they need those nutrients in order to survive, okay? What happens during El Nino is these trade winds weaken or they reverse. So now we get that warm water flowing backwards, and now South America is warm. And we don't have that cold, nutrient-rich water coming up. And because we don't have that nutrient-rich water, we don't get phytoplankton, and then the fishies die because there isn't as much phytoplankton. Okay? So one way that somebody explained it to me, this is my awesome drawing. Okay, there's a demo you can do that I was like, oh, we should really do this. And then I was like, no, this will be way too much effort. So what they do is they take like oil and they put it on the top, and this represents the warm water here, okay? And they color it red with oil, like basically oil-based paint. So, and then they have a hair dryer, okay? So this is normal conditions. That hair dryer is pushing all of that hot water, a lot of it, over to this side, right? And so over here we have Asia and Australia, okay? So it's really warm over here. In Peru, it's nice and cool, and we get all of this water upwelling, that cold, nutrient-rich water. This is normal conditions with the hair dryer because these are our trade winds. Now, then they turn the hair dryer off, and this is El Nino. So what happens is with that hair dryer off, we don't have those winds anymore. And so this hot water flows backwards, right? Because we have a whole bunch of hot water here. So it's going to even out. So now we get a whole bunch of warm water here. We don't have that upwelling. So it's going to be warmer by South America, and it's going to be cooler over by Asia. Okay? All right, so we're going to draw a diagram here. Do you guys need to write some of this down? Yes, no, maybe so.
You can do like an ASMR plus put the microphone.
What?
You never saw it?
Okay.
You see more.
We'll talk later.
ASMR.
Okay, so if we look at this diagram, this is during El Nino, right? We see it's wet and warm over in South America, and then it's dry over here, okay? So for the diagram that's in your notes, here's what we're going to draw, okay? It's a diagram in your notes. So this is for El Nino year. For an El Nino year, we have our trade winds, okay? Trade winds are going to be blowing, okay, up towards the equator, right? Here's Peru, where we talked about the little fishies. We also will see those trade winds, right? They're still here as well, okay? So on this side, we have, it's going to be, you know, generally cool. Over here, we've got the warm water being pushed to this side. Okay, so I'm just going to write that the warm, wow, that's warm, pretend that says warm. Warm water is being pushed this way, okay? Now, when we get an El Nino year, I apologize, this is the normal year up top. El Nino year, sorry guys, sorry. That's normal. An El Nino year, they weaken. I know. I can't ever make mistakes, can I? So normal, and then we have, and during El Nino year, they weaken, so it's going to go in the opposite direction. And so Peru's going to end up being warm, and it's going to have a lot of rain, so it's warm and wet. The other side's going to be cool. So now our warm water is flowing back in the opposite direction. And this causes, it's not just in the Pacific Ocean, right? This is where it happens, but it actually causes lots of different things to happen all around the world. We get affected, like the coast of California gets affected, and the United States from El Nino as well. All right, here's what we're going to do, okay? At your desk, you are going to be working with the person next to you, okay? Josiah, you can work with Vinny. And you are going to be drawing a diagram, okay? I'm going to give you this. This has like a template of a diagram that you're going to be using. These are lake zones. So we were going to do like this whole like terrestrial speed dating biome stuff. We're going to save that for a couple days because I need to plan, and like half of my 5th hour didn't turn in their worksheets. So I have a bunch of them. If you did not turn in your worksheets, get them to me because I have to like plan where you're going to like sit. It's like this whole orchestrated thing. Anyways, so we're just going to push that back to Wednesday and Thursday and just flip-flop what we're going to do then to now, okay? So we're moving to, we're skipping terrestrial biomes till Wednesday, and we're moving to aquatic biomes. So talking about different aquatic biomes, so freshwater biomes, lakes, ponds, marshes, and there are different zones of a lake that you need to know. And there are quite a few AP questions that show up on zones of lakes or zones of oceans. So here is a blue sheet that you're going to use. You're going to be creating a diagram on your desk. I have chalk markers. Okay, so I'll come around and give you a chalk marker. Create a diagram on your desk of these different zones. Okay. The one thing I will say is I did not put the profundal zone on here, but I meant to. So when you are looking, this bottom zone, let me show you a picture here. Does everyone see this bottom zone? Zone very at the bottom? This is the profundal zone. I did not put a description on here because I forgot and apparently was doing this late at night. So the profundal zone is the very bottom one. So when you go to make your diagram and you label it on your desk, just know that the bottom one is the profundal zone. Okay? The one that's, it's not the one that has like the arrow that's off to the side. It's just the bottom layer there. Okay?